My dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I would like to welcome you all to our International Physics webinar. Good evening to all. Hope you are well and safe from Corona pandemic. So it's very difficult for us to continue our normal academic program inside the campus. So we have to start our online program. I think you have already come to know that the Department of Physics, Pabna University of Science and Technology has started its online program, including online international physics webinar, and we have successfully completed our 201 international physics webinar. Today it's our 202nd international physics webinar, and today we have with us here Dr. Aragam Prasanna sir, Senior Professor Physical Research Laboratory, Ahmedabad, India, and he has already connected with us. So I'd like to welcome our speaker. Good evening, sir, and thanks for joining with us, and thanks for accepting our invitation. So dear students and viewers, I think you have already come to know the title of this today's international physics. The title is the Modern Astrophysics, and it's the beginning. Very exciting title. I think you will enjoy it. And our speaker is Dr. Aragam Prasanna sir, Senior Professor Physical Research Laboratory, Ahmedabad, India. So sir, it's your time. You can start your session, and we'll take question later in our discussion session, sir. Okay.
Sure. Thank you very much for this nice opportunity for me to address.
It's my pleasure.
Gathering. Can you hear? Hello?
I can hear. Yeah, you can carry on, sir.
I'm very happy to be here with you all, share my thoughts and my little ideas about the modern astrophysics and its beginnings. Let's start. We all have heard this pretty song, Twinkle, Twinkle, Pretty Stars, how we wonder what you are. And look at that, isn't it beautiful? Now, Galileo's telescope gave us a new view of the solar system. It helped us see the Jupiter's moons, Saturn's rings, outer planets, as well as the Milky Way. With the improved technology, our visual universe covered hosts of galaxies, clusters, and stellar systems of this type. Now, in 1930 came the revolution of the enigmatic radio universe, led by Carl Jansky and G. Reber, which uncovered very high energy cosmic sources like quasars, active galactic nuclei, pulsars, and more importantly, the most profound, all-encompassing cosmic microwave background radiation, which is indicative of the Big Bang universe. Now you see the quasars, galaxies, and this is the background radiation. While observations are the most important aspect of understanding the universe, one needs to understand the science of the processes that lead to make these objects visible or recognizable. Earliest among the theory of cosmic emissions is the process of nucleosynthesis, formation of elements that makes the star visible. The visible structures that are present are mainly made up of clouds of hydrogen, the element most abundant in the universe. Inside these molecular clouds, the hydrogen atoms move randomly, get very cold, and just try to huddle with each other. Luckily, gravity helps them, and it makes it closer, and so the whole core starts becoming smaller and smaller. As they become smaller, then the particles start moving faster and faster. And as they move faster and faster, they hit with each other, and then it starts like two hydrogen atoms combine to form the next one, deuterium, and a third hydrogen atom joins them to form tritium. And then a fourth hydrogen atom combines with this and makes it the four hydrogen atom combined gives you the helium, the element with 2 neutrons, 2 protons, and 2 electrons. Incidentally, this, as you all know, the energy source of our sun is due to this process of fusing hydrogen to form helium. In fact, the name helium was given to this element because it was first discovered in the sun, and the Greek word for sun is helios. This discovery was made by the astrophysicists Piers Jules Caesar Janssen and J. Norman Lockyer from observations made from the spectral lines taken by the Kodaikanal Observatory in South India in the year 1868 during a solar eclipse. During all these processes, lots of heat energy gets liberated, and this heat energy comes out as radiation. What next? At this stage, our original molecular cloud has shrunk to a very small volume because of gravity. But then, with the help of the pressure coming from the radiation opposing gravity, a stable form is obtained, which becomes visible. A star is said to be born. This process inside a star carries on for hundreds of millions of years. And as most of the hydrogen gets turned into helium in the core, the helium burning starts to produce carbon, nitrogen, oxygen, and so on, the higher elements in the periodic table. Now, the process of forming newer elements through fusion of nuclei is called nucleosynthesis. The hydrogen which is left in the outer shells of the star still burns, and this makes the radiation pressure become so enormous that it takes over gravity and starts expanding the star to a large volume. As the radiation cools due to expansion, the star appears red and is called a red giant. Now, this is the first direct image of a star other than the Sun made with NASA's Hubble telescope. Now, Alpha Orionis or Betelgeuse, it's a red supergiant star marking the shoulder of the winter constellation Orion the Hunter. The Hubble image reveals a huge ultraviolet atmosphere with a mysterious hotspot on the stellar surface. The enormous bright spot, twice the diameter of the Earth's orbit, is at least 2000 degrees Kelvin hotter than the surface of the star. Betelgeuse is so huge, if it replaced the Sun at the center of our solar system, its outer atmosphere would extend past the orbit of Jupiter. Now, in the inner core, the nucleosynthesis continues till all the elements fuse to form the element iron. As you all know, iron is the most stable element, and it cannot fuse with anything else to form any more element. And therefore, the burning stops, core becomes cool. Then again, gravity takes over and starts shrinking the core to a smaller size. This is called the gravitational contraction. During this phase, the outer envelope gets ripped off the star in a wispy shell, which is called a planetary nebula. Now, there are examples of planetary nebula. This is called ring nebula, blue snowball, this is dumbbell nebula, and this is cat's eye nebula. Now, this is more interesting because this is called boomerang nebula, and this picture was taken by the NASA ESA Hubble telescope, and it is in the constellation of Cetus, 5,000 light years from Earth. In 1995, using the 15-meter Swedish ESO sublimated telescope in Chile, astronomers revealed that it is the coldest place in the universe found so far, with a temperature of around minus 272 degrees centigrade or 1 degree Kelvin. Interesting, isn't it? Now, when the iron core collapses, there will be so little space between the atoms that the electrons in the atom get freed from the nuclei and the whole core becomes enriched in the free electron gas. In 1930, S. Chandrasekhar, the Indian-born astrophysicist working at Cambridge, studied this aspect of stellar evolution carefully using the then newly developed theories of quantum mechanics and special relativity, and discovered that such an electron gas core would be stable if and only if the mass is less than or equal to 1.4 times the mass of the Sun. In such a case, the pressure due to the free electrons would be adequate to oppose the gravitational infall, and the remains of the star would become what is called a white dwarf, a dead star. The mass limit of 1.4 times the solar mass for a white dwarf is known as Chandrasekhar limit, for which discovery he received the Nobel Prize for Physics in 1983. Now here are some examples of white dwarf stars in M4, and this nearest globular cluster to Earth contains more than 100,000 stars. M4 was the target of a Hubble Space Telescope search for white dwarf stars. Ancient red giant stars are predominant in this view from a ground-based telescope. The field is 47 light years across. The box on the right side shows the small area of the Hubble telescope looked into. Now, Hubble reveals a total of 75 white dwarfs in one small area within M4, out of the total of about 40,000 white dwarfs that the cluster is predicted to contain. The Hubble results will allow astronomers to refine theoretical predictions of the rate at which the white dwarfs cool, which is an important prerequisite for making reliable estimates for the age of the universe and of our Milky Way galaxy based on white dwarf temperature. Now, if such a scenario occurs in a double star system, a binary system, with one of them becoming a white dwarf, while the other is still in the giant phase, then because of the smaller dimension of the white dwarf, it starts pulling matter from the companion. This matter, as it falls onto the surface of the white dwarf, the star ignites and shines brightly for a while. When one sees it from Earth, it appears as though a new star has just appeared, and hence it is called a nova. This high-resolution HST image of the nova demonstrates that not all classical novae are alike. The ejectae of most novae are expanding gaseous shells. The ejecta of this nova consists of some 2,000 gaseous blobs in a volume of 1 light year across. Now, in this process, if a large amount of matter gathers on a white dwarf, then again gravity can take over, and the white dwarf starts collapsing. At this stage, as in the core there were lots of free electrons, they get pushed into the nuclei, and electrons and protons combine to form neutrons, adding a large number of neutrons to the already existing ones, thus making the core neutron rich. However, the burden of additional mass falling on the white dwarf makes it unstable, with gravity taking over to implode the entire core. The sudden implosion of the core triggers an explosion of the entire star in a big boom, which is called a supernova. Now, here is the example of a wild supernova. It's called a wild nebula. It is the remnant of a supernova explosion that could have occurred about 5,000 to 10,000 years ago. It is located about 1,400 light years away in the constellation of Cygnus, NGC 699295. Is the brighter eastern half of the nebula at left. NGC 6960 is the portion of the SNR that appears close to the star 52 Cygnus on the right half arc. Analysis of the emission seems to indicate the presence of oxygen, sulfur, and hydrogen. Now, here is the one which luckily people could enjoy seeing it. This happened in 1987. Now, here is the example of the supernova. The glittering stars and wisps of gas create a breathtaking backdrop for the self-destruction of a massive star, supernova 1987A, in the Large Magellanic Cloud, a nearby galaxy. Astronomers in the southern hemisphere witnessed the brilliant explosion of this star. This was the before, and this is after. And this is the picture taken from a wide field camera on September 1994, February 96, in July 97. It's a mosaic. The many bright blue stars nearby the supernovae are massive stars, each more than 6 times heftier than our Sun. They are members of the same generation of stars as the star that went supernova about 12 million years ago. The presence of a bright gas cloud is another sign of the youth of this region. It still appears to be a fertile breeding ground for new stars. Now, the core of the star, which imploded to a small size, would end up as a neutron star. Because it is full of neutrons, that would happen, and it would be in stable equilibrium with the neutron degeneracy pressure acting against gravity, provided the mass of the core is about 4 to 5 solar mass. A typical neutron star of mass 1.5 to 2 solar mass would have a size of approximately 10 to 20 kilometers radius. The density of a neutron star is enormous. A teaspoonful of neutron star matter would weigh about 100,000 tons. Pulsars, discovered in 1967 at Jocelyn Bell of Cambridge, are supposed to be rotating neutron stars emitting a beam of electromagnetic radiation, which appears as a pulse on observer's antenna. Here is the first recording of the pulsar. Now, what is the pulsar electrodynamics? The rotating neutron star has a very high magnetic field. Where did it come from? Mainly because as the star is collapsing, the magnetic field of the star gets trapped, and during the collapse, and subsequently a well-defined magnetosphere occurs. The magnetic axis is inclined to the rotation axis. Now, charged particles from cosmic rays get trapped along the magnetic field lines and produce a radio beam as shown in the picture. As the central star is rotating, in every revolution, the beam intercepts the line of sight of the observer, and that produces a signal which repeats itself in synchronization with the rotation speed of the star, producing a sequence of pulses. Now, here are some pictures of the most famous Crab Nebula, which also has a pulsar. This is the nebula in the optical frequency, in radio frequency, in ultraviolet frequency, and in the X-ray frequency. The X-ray image of the crab was taken in the fall of 1999 as part of an observation by Jeff Hester and collaborators using the Chandra X-ray Observatory in space. It revealed for the first time a small ring around the Earth. The Chandra image also shows in higher resolution the jets and larger outer rings which had been previously discovered by Rosette. Now, what if the mass of the collapsing core is more than 5 solar mass? So we have the story up to, now if it is 1.4 solar mass, it will become a white dwarf. If it is 2 to 3 solar mass or 4 solar mass, it becomes a neutron star. But what if the mass of the collapsing core is more than 5? Then even the neutron degeneracy pressure would be incapable of preventing the gravitational infall. The whole star would collapse under its own weight inside its event horizon and become a black hole. A black hole is a region of space-time where a very heavy star, mass greater than 10 solar masses, collapsed due to its own weight and has potential energy so strong that it simply captures everything that falls on it. The gravitational attraction of this object is so very strong that even light gets bound or trapped by it. Hence, unlike in the case of other stars, as no signal can escape from it, it cannot be seen directly and thus called a black hole. There seems to be strong evidence for two types of black holes. Stellar black holes with masses of a dozen or so suns, and super black holes with masses of many millions of suns. Now, stellar black holes could have formed as a natural consequence of the evolution of massive stars. The origin of supermassive black holes is still a mystery. They are found only in the centers of galaxies. It is not known whether they formed in the initial collapse of the gas cloud that formed the galaxy or from the merger of a centrally located cluster of black holes. We have seen that the compact star that collapses to black hole. Oh, incidentally, somebody may ask a question like, if black hole cannot emit anything, how do we see it? How do we visualize it? Now, here is the story. When it collapses, normally what happens is it has also a giant companion. And black hole, because of its enormous gravitational pull, pulls the matter from here. And that matter comes and forms an accretion disk. A disk. And then the inner regions of the disk get so hot, it emits electromagnetic radiation in the X-ray frequency, which can be observed through X-ray telescopes like Chandra, Uru, Exosat, Rosat, and Einstein Observatory. Since its launch on July 23, 1999, the Chandra X-ray Observatory has been NASA's flagship mission for X-ray astronomy, taking its place in the fleet of great observatories, particularly for the physics of black holes. Now, we know that neutron star also is a compact object. Black hole is, of course, a compact object. Now, supposing there is accretion on both of them, how do we distinguish the two? Now, what is the comparison? Here it is. As the gas nears the event horizon, a strong gravitational redshift makes it appear redder and dimmer. When the gas finally crosses the event horizon, it disappears from the view because a black hole has no surface. The central region is black. On the other hand, in the case of a neutron star, as gas approaches the neutron star, a similar gravitational redshift makes the gas appear redder and dimmer. However, when the gas strikes the solid surface of the neutron star, it glows brightly. Now, here is the story of the stars. Low to average mass, less than 1.4, Chandrasekhar, it's a white dwarf. Large mass star, 1.5 m to 4 to 5 solar mass, neutron star. Very large mass star, mass greater than 5 to 10 solar mass, becomes a black hole. While it is possible to view the universe both in radio and optical windows from the Earth, because of the life-protecting atmosphere, the radiations from cosmos in other frequencies, except a little of IR and microwave, do not reach the Earth. One needs to go outside the atmosphere to receive the radiation in other frequencies, and thus one had to wait till the advent of space technology, rockets and satellites, to look at the violent but beautiful universe in the entire electromagnetic spectrum. This became possible in the mid-60s, and afterwards the phenomenon. Though the X-ray emission from the sun was known from early days through high-altitude balloons, the first cosmic source, Scorpius X1, was detected in 1962 on board a rocket. In 1960, the first dedicated X-ray satellite, Uhuru, was launched to make a sky survey for X-ray sources in the 2 to 20 keV range. In 80s and 90s, advanced rocket and satellite technology led to several missions from the US, Russia, and Europe, saw a gamut of observations in all frequencies from IR to gamma rays, and our view of the universe expanded billionfold in understanding the physics of the cosmos. Prominent among them were the IRAS for the IR survey, Hubble for optical telescope, IUV UV survey, Chandra for X-rays, Kobe, WMB, and Planck for background radiation, and Compton Gamma Ray Observatory, launched in 1991. Results from all these and several other space missions helped the astrophysicists and cosmologists to model the universe and the varied physical processes that govern the emissions. Anybody wanting to ask a question at this stage?
Okay, sir.
Any questions?
Yeah. So we
Yeah.
have got two questions. First
Yeah.
is what is the boomerang nebula, and another is what are the difference between the stellar and the supernova black hole?
Sorry, I couldn't understand. What is it? What is the difference between?
Boomerang nebula. What is boomerang nebula?
Oh, it's just one of those, most of the nebulae are molecular hydrogen clouds. And this one, the shape of the nebula is such that they call it a boomerang nebula because it looks like a boomerang. That's the reason. But the point is, it seems to be the coldest place in Earth because the temperature astronomers have verified in the sense of whatever observations they have made using the spectral lines, they can work out the little bit of thermodynamics of that. And from that, they find temperature to be 1 degree Kelvin. So as far as we know, there is no other example which is so cold in the universe. So it could be the coldest place. And other question about black hole?
Yeah, what are the difference between the stellar and supernova black hole?
Smaller and bigger black holes? Or
Stellar and supernova.
Stellar. Oh, okay.
Yeah, stellar.
Stellar black holes. There are black holes of different masses. There are stellar mass black holes. That means if it is only about 50 to 100 solar mass black hole, then it's called a stellar black hole. If it is more than that and it goes to beyond like about a million black holes, a million times the mass of the sun, then it's a bigger galactic black hole. It's a supermassive black hole. Supermassive essentially is a much, much bigger and much, much massive than stellar black holes. And also, as I said, stellar black holes, probably they formed by the collapse as we described the collapse. But supermassive black holes, it is still not known how they formed. There are different theories. Some people feel that already in the galactic core, there was a black hole. It starts at when other black holes and it became a huge supermassive black hole. That's a theory. These are very difficult to confirm. In astrophysics, one should always say, that whatever we have, the evidence, from that it may be so. You can never say it is so. You can't use the verb is in the case of astronomy because we cannot just go and check out anything. And also you cannot repeat the experiment. Therefore, one day we can say it may be, and if a similar theory works, and supposing we are able to predict something and see that it is there, then we say the theory is right. That's the way we do. Okay. Now let me continue. Now, of all the discoveries of the human mind, Einstein's theory of general relativity is considered to be the most beautiful creation. In fact, it is said that the special relativity, which forms a strong basis for modern physics, along with quantum mechanics, was ripe to be discovered at the turn of the 19th century, and if not Einstein, Poincaré or Lorentz would have developed the theory. On the other hand, the general theory of relativity, which is the epitome of the world of symmetry, assigning freedom from the confines of coordinate systems to understand the most important of all fundamental interactions, gravity, is completely the work of one individual, arising out of thought experiments instead of laboratory experiments or observations that preceded all other discoveries in physics. I said about thought experiment. Now, what do we really mean? Now, Einstein, as you know, he first formed special relativity in 1905. And then for the next 80 years, he was in search for a more general aspect of relativity where he could bring in gravity and the forces. And so he then thought he used two things. One is the equivalence of inertial and gravitational mass of any body, known as the principle of equivalence, now demonstrated by Ertwas. Now, what do we say in this? The thought experiment of Einstein was as follows. Supposing you are in a lift, and then somebody breaks off the cable. It's freely falling. Then now you take a coin from your pocket and then put it there. What happens? You expect the coin to reach the bottom of it, but it won't, because the lift and this are both coming at the same acceleration. And therefore, this gives Einstein the idea, this force is same as this force, this mass are equivalent by this in principle of equivalence, and therefore A equal to G. That means gravity is an acceleration. Now, this is fine. It's almost being said that there is no gravity here, which is something which we all know. For example, in the case of astronauts who are moving in the space, within their regions, they know that they'll be flying. They can't walk. Now, supposing instead of one coin, you put two coins, 1 and 2 like this. Then what happens? Very interestingly, the coins not falling down, but they are coming closer to each other. How does that happen? See one like this. Very simple. Look at the picture here. Now this is the Earth, and we all know that center of gravity is in the center of the universe, center of the gravity here. And now these coins are following their geodesics, which are these lines going to the center, and these lines are converging here. And therefore, as they fall coming down, these loops appear coming closer. This shows that there is a relative acceleration between the particles. The second was the effect of gravity on light, which is called Einstein redshift. Here again in the lift, supposing a friend of yours standing here, and he opens a torch, beam of torch. And now, within here, you will see this coming as OA, but somebody staying out will see it coming as OA prime, because this is falling. Therefore, the line is bent here. And more interestingly, we know that bending of light by gravitational field. Therefore, he knew that there is an effect of gravity on light, and one needs to consider that when taking how to introduce the new or generalized theory of relativity. Now, supposing he wanted to construct it along with special relativity in the same framework. The special relativity framework is a Minkowskian framework, which is a flat framework. And therefore, the light beam's rays would be parallel lines like this, and in principle it should be delta T1 equal to delta T2, which means the frequencies should be the same. But what one finds is F1 is greater than F2. Therefore, F1 delta T1 must be smaller than delta T2. That means the light rays don't go like this, but they go along the curves. Now, this one said, Einstein realized that the arena he wanted for general relativity was the non-Euclidean geometry, a requirement satisfied by the Riemannian geometry, an extension of Gaussian curved geometry. It is metric. The intrinsic curvature of a Riemannian space, represented by the curvature tensor, represents the acceleration between two freely falling particles, thus representing gravitation. Now, so if we take particles, then world lines should be like this as curves. If you take any two of them and take a vector like this, eta I, and you find what is the acceleration between these two. Now, Newtonian theory tells me that the acceleration would be minus eta k delta A phi, where phi is the gravitational potential. But in Riemannian geometry, what we have is these are called equation of geodesic deviation. This means that you see if you have a geodesic, then it is made a small deviation. The equation it would follow is this. Now this is a very geometric equation. In order to understand this, we need to do a little bit of exercise. What one does is you take this into, you introduce what is called a locally, I had to go back here. I'm sorry for a minute. Wait a minute. Here it is. It's fine. I'll have to just check this out. 1 minute. 1 minute, please. Yes. Yeah. A vector, the geometrical vector, is resolved as lambda IA xa. Now, in general relativity, since we already have the equivalence principle, there is something called strong equivalence principle, which says that at every point in the curved spacetime, you can introduce a tetrad, a 4 vector for x, y, z, t, such that the physical components of the vector can be idealized. Since this is the flat 4 tetrad, I get here, and therefore I can get in terms of xa. And now, so I get this equation in terms of xa and curvature tensor Rxab. So this is the relative acceleration between two particles. Now, this is a very important thing, because now as you go, sorry about this repetition. Okay. Now the field equations of general relativity satisfy the equations Bianchi identities and consequently the conservation laws. As these equations are highly nonlinear and coupled set of partial differential equations, it is difficult to look for general set of solutions analytically. In fact, Einstein himself in 1916 had suggested that one could look for solutions in linearized approximation, assuming Gij to be eta ij plus hij. Outside the matter distribution, the field equations reduce to Rij equal to 0, which gives in the Lorentz the same wave equation of Hij equal to 0. Now this has a solution to this form with A in the complex amplitudes which are symmetric and Ki the wave covector satisfying the orthogonality relation like this. The gauge condition yields 4 constraints on the 10 complex amplitudes, all of which in turn will be expressed through the metric potentials in this form. Consequently, one finds that the plane gravitational wave have only 2 degrees of polarization, generally denoted as plus and cross polarization, and carry energy proportional to the sum of the squares of the amplitudes as expressed by the component of the Isakson tensor. What I'm trying to explain here is, that basically these equations are complicated. There are several solutions which we are not going to discuss. But the most important thing is the linearized approximation gives us the result that there can be gravitational waves, plane gravitational waves with 2 degrees of polarization. And then, now, how do we know about that? What do we do? Now consider a ring of test particles like this. Now and then you expect a gravitational wave to pass through this ring of particles. Now, if eta I is given by this relation, this vector, and if it is such that we have a plus polarization of the gravitational wave, then what happens is this ring of particles will oscillate like this. On the other hand, if eta is this, which means we have a cross polarization, then they will oscillate like this. So a ring of particles, when meeting a gravitational wave, starts moving like this or this. So there is a vibration system in the system. This is exactly what one needs to consider in order to detect gravitational waves. Now, Joe Weber was the first to really think of detecting gravitational waves, and in 1960, he started working on it. It's a cylindrical antenna, a cylindrical drum actually, of aluminum, and there are photodiodes here. And now he thought that when the gravitational wave passes here, then these diodes will be activated and that will give a signal. And if he has another punch of a similar kind far away, if there is a simultaneous signal in both, then he thought he would have found the signal. In 1967, he even thought that he had recorded gravitational waves, but unfortunately, that turned out to be not so. But no problem. The first successful indirect detection of gravitational wave was from Hulse-Taylor binary pulsar, which was discovered in 1974. Now, it was predicted that the binary orbit would shrink due to the continuous emission of gravitational waves, which carry away the orbital energy. Now, continuous recording of the pulse arrival time year after year, it confirmed the shrinking of the binary orbit due to emission of gravitational waves. By 1982, the pulsar was arriving at its pre-astron more than 1 second earlier than would have been expected if the orbit had remained constant. Now, data in the first decade after discovery have shown a decrease in the orbital speed of about 76 billionths of a second per year. Thus, so the first beautiful confirmation of the existence of gravitational waves came through the binary pulsar. Now, as the orbits shrink, the binary components inspiral and coalesce finally, giving rise to a catastrophic event, which can produce a huge flux of gravitational radiation. The HT binary will coalesce in about 250 million years. Coalescence of massive binaries are among the strongest sources of gravitational wave signals, with energetics measurable by the ground observations. Now, black hole mergers are the best candidates. Now, two black holes when they coalesce and match, there are three phases. It's called in-spiral, merger, and ring down. Now, during the in-spiral phase, the orbits of the binary components get circularized due to emission of gravitational waves, and the components spiral together in quasi-circular orbits, and the orbital timescales will be much shorter than the timescales on which the orbital parameters change. Peak field approximation is valid only before the merger phase, and thereafter, the strong field general relativistic effects come into force, and one has to adopt numerical methods and computer simulations for building the templates for signal matching. What we mean is, it was fine to test with the binary pulsar, the plane gravitational waves, was a peak case, gravitational. But the two black holes coalescing is an extremely strong gravitational event, and fields are extremely strong, in which case Newton's theory will not be sufficient. You need to introduce something more sophisticated and work out the thing. Now, this is what the LIGO observatory does. LIGO, Laser Interferometer Gravitational Wave Observatory, it has 4 masses are hung on a vibration-free system, with their separation being monitored by a highly sophisticated optical system. The two arms are of almost equal length, such that delta L to L1 minus L2 is directly proportional to the output of the photodiode. When a gravitational wave having frequency higher than the pendulum's natural frequency of about 1 Hz passes through, the relative acceleration induced by the wave pushes the masses. As I showed you, with the particles, the gravitational wave makes the particles vibrate, and that will make these masses move, and that makes a small change in these distances. And therefore, depending upon the polarization of the impinging wave, the interferometer's output would be a linear combination of the two fields, as given by this. Now we have solved the order of unity having quadrupolar dependence upon the direction and orientation to the source, and actually the strain of the wave with their time evolution giving the waveform. Now, how would the waveform look like? A typical waveform coming from an inspiraling binary system, computed using Newtonian gravity for the orbit evolution and quadrupole moment approximation for wave generation, would look like what is shown in the figure. Now, where one finds that as the inspiraling gets closer, the amplitude increases and one has an upward sweeping frequency of the waveform, which is called a chirp, with amplitude ratio for the polarization going as this. Now, the orbital eccentricity determines the harmonic content of the wave. Thus, one can, by measuring the two amplitudes, frequency sweep, and the harmonic content of the inspiraling wave, determine the source's distance, chirp mass, inclination, and eccentricity. The final phase is the ring down phase. When the merged black holes could form a highly distorted single black hole, which may finally settle down to a Kerr black hole, smoothing itself after shedding all the non-axis symmetric modes by emitting gravitational waves in the form of quasi-normal modes characterized by mass and spin of the black hole only. Working out the dynamics of this final phase is one of the most challenging problems of numerical relativity, as it deals with the black hole perturbation theory. Perturbations of Schwarzschild black hole studies were initiated by C.V. Vishveshwara in 1970, extended by Zerilli, and perturbations of Kerr black holes studied by Tarkovsky. Now, for a full formalism of black hole perturbations, we have Chandrasekhar et al. Between 70s and 80s, which is finally summarized in the book Mathematical Theory of Black Holes by Chandrasekhar. Now, further work by C.M. Will on post-Newtonian approximation and parameterized post-Newtonian schemes helped the understanding, while Damour and Iyer worked on approximation methods during 80s and 90s that became significant for analysis. Template construction for match filtering techniques were developed by Satyaprakash and Dhurandhar in the 90s, and a big step in numerical relativity was achieved by Paulus in 2005, which indeed initiated the serious attempts to detect the gravitational radiation on Earth with the advanced LIGO detectors, which were indeed developed in the late 80s with serious efforts put in to increase the accuracy throughout the 90s and early decades of the present century. Finally, it was in September 2015 that a positive identification was made of the gravitational wave signal simultaneously in two of the LIGO detectors, which was also confirmed by the Virgo detector. Now, here are the signals. Now, these are the signals recorded at that time. The gravitational wave event is called GW 150914. It says that it is 14th of September 2015. Observed by LIGO, Hanford, left column, and Livingstone. Now, these are times are shown. The signal is due to gravitational wave emitted by the merger of two black holes of masses 29 solar mass and 34 solar mass, finally resulting in a black hole of mass 60 solar mass. At at a distance of about 440 megaparsec, equivalent to about 1.4 plus or minus 0.6 billion light years. The chirp signal lasted over 0.2 seconds and increased in frequency and amplitude in about 8 cycles from 35 Hz to 250 Hz. The signal is in the audible range and has been described as resembling the chirp of a bird. The total energy radiated from the collision seems to be equivalent to 3 plus or minus 0.4 solar masses. While 2 other events of gravitational wave detection were announced in December 2015 and January 2017, the most significant announcement came on 17 August 17. It was attributed to the gravitational waves emitted from the collision of 2 neutron stars. And along with the gravitational wave, electromagnetic signals were also reported in all parts of the spectrum, gamma rays to radio frequencies, from the same part of the sky as this. It's a beautiful thing. See? So X-ray, UV, optical, IR. So it showed in everything. Now, this has been very fortuitous, as coordinating all these observations would help in modeling the source, particularly the distance, to help the understanding of neutron-star coalescence, which rakes up a new era with multi-frequency astronomy. Some of the very important questions that one needs to ask and investigate are as follows. As neutron stars have associated magnetic fields, it is necessary to study and model the magnetic dipole interactions and their topologies. Would there be a possibility of a resulting toroidal magnetic field around the final object, which could trap the plasma resulting from the debris of collision? And if so, what would be the signature of high-frequency emission coming from within the region passing through this plasma? Will there be secondary emissions from the plasma in lower frequencies with finite time delays? One could, for a beginning, do these analyses in special relativistic formalism and then try to extend the studies to curved background, as the gravitational field associated with the final objects would be very high. The interactions of the gravitational electromagnetic radiation is also important to investigate, particularly when both are coming from the same part of the sky, as there would be the effect of gravitational field of the waves on the propagation of electromagnetic radiation. And the new era for astronomers and astrophysicists is nudging them to make more sophisticated and more sensitive instruments to look at the cosmos from radio waves to gravitational waves. Adopting new technology, physicists are urged to look for new signs of model building for understanding collisions of binaries with black holes and neutron stars, and the resulting debris, which could emit all forms of radiations one is familiar with, but do not fully understand their generation and propagation. Another important aspect of modern astrophysics is the study related to dark matter and dark energy. If one considers a pie chart of the matter and energy in the universe as shown, the comprehensible matter that we can identify through all our instrumentation seems to fill only less than 5%. About 26.8% is attributed to dark matter, while the bulk of 68.3% is supposed to be occupied by the dark energy. Now, what is dark matter? Originally known as the missing mass, dark matter's existence was first inferred in 1933 by astronomer Zwicky, who discovered the mass of all visible stars in the Coma cluster of galaxies provided only about 1% of the mass needed to keep the galaxies from escaping the cluster's gravitational pull. Thus, he initiated the idea of missing mass that would be required to account for the observed velocity of stars. The reality of this missing mass remained in question for decades, until the 1970s, when American astronomers Vera Rubin and Ford confirmed its existence by observation of a similar phenomenon. The mass of the stars visible within a typical galaxy is only about 10% of the required to keep the stars orbiting the galaxy's center with a mass to luminosity ratio 9 by L 10. Where is the rest of the mass supporting these orbits? This phenomenon was noticed in most galaxies as having rotation curves showing solid body rotation in the very center, followed by a slowly rising constant velocity rotation in the outer parts. This feature of flat rotation curves was interpreted as implying that the increasing or constant velocity has to be compensated by some unseen mass, which increases linearly with the radius. If there were no mass originally from Newtonian theory, it should have been simply like this. But the observation shows this. It is starlight, and this is from 21 centimeter hydrogen lines. In general, the speed with which stars orbit the center of their galaxy is independent of their separation from the center. Indeed, orbital velocity is either constant or increases slightly with distance rather than dropping off as expected. To account for this, the mass of the galaxy within the orbit of the stars must increase linearly with the distance of the stars in the galaxy's center. However, as no visible signal is received from this inner mass, the notion of dark matter was confirmed. However, the bigger question is, what are the constituents of dark matter? If it were to be baryonic, then the only form there could be is as brown dwarfs or white dwarfs, neutron stars, or black holes. But then one would expect these to act as gravitational lenses for stars and galaxies behind them, which would become observable. Now, more popular belief is that dark matter is composed of non-baryonic matter. However, the leading candidate, WIMPs, weakly interacting massive particles, which have 10 to 100 times the mass of a proton, failed to get confirmed due to their weak interactions with normal matter. Neutralinos, neutral gauge, and scalar bosons, massive hypothetical particles, heavier and slower than neutrinos, are the foremost candidate, though they are yet to be detected. Sterile neutrino is another candidate, but again difficult to observe as its interaction is restricted to gravitation only. The hunt for dark matter is progressing with newer attempts to devise instruments and sensitivity detectors, which may yield positive results or lead one to look for revising the theories of orbital dynamics with newer interactions. The more intriguing question relates to dark energy. Dark energy is mysterious, and its discovery in the 1990s was a complete shock to scientists. Physicists had assumed that the attractive force of gravity would slow down the expansion of the universe over time. But when two independent teams tried to measure the rate of deceleration, they found that the expansion was actually speeding up. Scientists now think that the accelerated expansion of the universe is driven by a kind of a repulsive force generated by quantum fluctuations in otherwise empty space. In 1998, two teams of astronomers announced that distant Z-zone type 1A supernova were slightly too faint than model predictions of an expanding universe. This faintness was attributed to the observed supernovae being farther away, which could indicate that the expansion of the universe was slower in the past. It was thus argued by both teams that presently the universe is going through a phase of accelerated expansion, and the cause for this accelerated expansion is the presence of dark energy. The infamous cosmological constant lambda, originally introduced and removed by Einstein, but later interpreted as representing the vacuum energy of empty space, can be attractive or repulsive depending upon its sign in the equations, resulting in decelerating or accelerating the expansion. In the 90s, after the supernova data, the idea of quintessence, a low energy field, gained popularity as a candidate for the dark energy. Whereas lambda is a specific form of vacuum energy, quintessence is dynamic, time evolving, and a spatially dependent form of energy, a quantum field with kinetic and potential energy. Conclusions. While the new era for astronomers and astrophysicists is nudging them to make more sophisticated and more sensitive instruments to look at the cosmos from radio waves to gravitational waves and new technology, physicists are urged to look for new signs of model building for understanding collisions of binaries with black holes and neutron stars, and the resulting debris, which could emit all forms of radiation one is familiar with, but do not fully understand their generation and propagation. Also, there are other aspects from the invisible universe of dark matter and dark energy which are not visible to the electromagnetic window but can be highly influencing the gravitational window. The multi-signal objects require much clearer and detailed analysis of all possible electromagnetic and plasma processes on curved spacetime and may also be influenced by quantum mechanical processes under severe conditions of equations of state for matter and radiation. The new era undoubtedly heralds the younger minds to go in for new opportunities, both in experimental and theoretical studies associated with the physics of collisions of compact, maybe ultra-compact, objects like black holes and neutron stars. Thank you.
Thank you, sir, for your wonderful presentation and exciting. So we have got few questions. So if you allow, we can start our discussion session.
Yeah, sure.
Okay, so the first question, what is the in spiral merger ring down?
What is inspiring?
Yeah, in spiral.
I think just a minute. Let me take a picture of it and show. Here it is. For example, it starts from here. Then, as they come closer, the spiral, because what happens is the gravitational waves are emitted. Now, to begin with, these are like elliptical orbits like this. But slowly, as they are losing the gravitational energy of orbit energy from here, these elliptical orbits become circular. And then they are took together. This is the in-spiral stage. Elliptical to circular they become. That's the in-spiral.
Thank you, sir. We have another question. So, sir, to do modern astronomical research, which type of computer skill are needed?
Well, to be honest, myself, I'm not a computer man. I mean, I'm purely a mathematical physicist. So all my research life I've been doing mostly analytical solutions and very little of computers. But then I know that in fact that's exactly the point. You know, though in the 80s to make this LIGO observatory, Am I visible now? Okay. Now, I was telling about, the computer thing. See, what they do is they make templates. Now, templates are numerical templates they make. Different templates for different parameters. Now, you have the template is made from the mass, distance, and various other parameters, orbital frequency, so many things. So, using these parameters, they make thousands of templates and keep them ready. Now, when finally the signal is obtained, then they match this. They call match filtering technique. And to do that, in order to make these templates, you need extremely complicated computer simulation. So it's extremely important for students to get into this area, get a full knowledge of computation. Also because I must tell the youngsters, there is what is called LIGO India. Have antenna, LIGO antenna, in about 10 years' time. Data that would come in. So there, in fact, in about 10 years, there's a prospect of having a large number of jobs also to analyze this data. And so physics, mathematics, and computer science, all these three backgrounds will make them extremely capable, and they can find interesting and nice jobs and also good research opportunities. So I would suggest that they should read more about LIGO India and then try and concentrate their efforts on both physics and computer science.
Thank you, sir. This may be the last question. So, can dark matter be composed of more than one type of particles?
That's the problem. Possibly, because now, see, they thought that the supersymmetric particles are responsible. Now it has been almost clearly ruled out. So if it were being supersymmetric particle, then it would have had a host of particles. But that is not there now. Therefore, I am not very sure whether WIMPs are the present leading one. See, the point is there is no interaction. It's extremely difficult. We should have something to go with, some evidence. If I calculate few things, some numbers I get, I should have something to compare with. And so, observationally, we are still far behind. And then, of course, the astronomical observations are increasing exponentially. We are having lot new instrumentation and new techniques. So data is coming in different forms, but not exactly the one which is required for this analysis. I hope, I'm sure there are other experts who work on dark matter and dark energy as their field of interest, and they will be able to explain more about the present status of dark matter and dark energy. But I think it is still dark.
Thank you, sir. There is another question. This might be the last question. So, what are the neutrinos coming far from the cosmos can reveal about universe?
Then I couldn't understand. What the neutrinos coming from or from the cosmos can reveal about the universe? Well, it's not clear. Possibly because, as far as neutrinos are concerned, there's a lot of work going on. Now people are trying to detect them also. The point is, the data so far seems to be explained by whatever theory one is having till now. In what way? You have to say that the entire dark matter is essentially for neutrinos. I don't know whether that can be a real situation. Because see, they are weakly interacting particles again, and then they are uncharged, so there is no magnetic field effect on them, and they can just pass through everything. So it's a very difficult thing to really say whether it is coming from cosmos or from a closer. That's the problem.
Thank you, sir, for your wonderful presentation and discussion session. So I think the
Yeah,
student has learned a
as
lot
I
of
said,
things about the modern astrophysics and its beginning.
I can
So
send the
thanks.
file to you. I
Yeah.
can send the file to you, which you can share with people who ever want the file. They
Okay,
can
sir.
use it, no problem. All right?
Okay. I'll. Yeah.
Okay,
So
thank
thanks
you.
again. Yeah. Bye for today. Good night, sir.
Okay,
Please stay safe.
bye.